Thank you, Cecil. All right, everybody has a note packet in front of them. Nod your heads, yes. Yay, very good. All right, so today we're talking about using matrices to solve systems of equations. And the very first step to using a matrix to help us solve a system of equations is to rewrite the system of equations in matrix form. So we can represent a system of equations in the matrix by using the coefficients on the variables and the constants, the numbers that aren't attached to a variable, as the entries in the matrix. And below that you see an example. So we have a system, 5x minus 3y equals 12, and 2x plus 6y equals 15. The first thing you should notice is that these equations are written in standard form. In order to convert to a matrix, I want my equations in standard form, all of them. So ax plus by equals c, or ax plus by plus cz equals d. Write them in standard form, stack them one above the other. Yeah. You will notice that the coefficients on the x show up in the first column. So that first column is my x column. You'll notice the coefficients on the y show up in the second column. It's my y column. Where do the numbers at the tail end of that equation come from? The right side, yeah. These guys are my constants. Those guys are my constants. And you will notice that there is a vertical line down the middle where we had our equal sign in the equations. What we're doing is we're indicating the variables from the constants. Nice clear separation. So this matrix of coefficients and constants is called an augmented matrix. This is the matrix we're going to use to solve the system of equations. If you continue to do math, or you are going into physics or engineering, something along those lines, you may also see something called a coefficient matrix, which is just this part of the matrix. It's just the part of the matrix that has the coefficients, the left part, without the constant part. So it would be a 2 by 2 instead of a 2 by 3. We are going to stick to the augmented, because the augmented is going to help us solve the system. So first we're going to practice a skill, which is just writing that augmented matrix, because if you can't do that, you can't do anything else. So let's do some examples. So example 1 says negative 3x plus 2y equals negative 10, and negative 3x minus y equals negative 13. Set up my augmented matrix. Should be about as big as my system of equations. Number of columns represents the number of variables plus a constant. Number of rows represents the number of equations in my system. And then I start. And you should always put the variables in order that they show up in the alphabet. X, Y, Z, A, B, C. So this first column should represent the x's. What are the coefficients on my x's? -3 for both. Yeah, -3, -3. Good. Next variable should be the y variable. What's the coefficients on my y's? 2 and -1. Perfect. Notice if the 3's here didn't match, it would be important that these match across. The rows have to come from the same equation. Good. Constants. -10, -13. Perfect. Take a second in your small groups. Do the same thing for example 2. Give you about 90 seconds. My other classes liked your example of your snake, by the way. They all commented it was nice that it wrapped around. That was a creative solution to the problem. All right, do I have a volunteer who wants to come up and write the matrix? No one's quick, so we're going to call a name. There's my name generator. Chris is not here. Emiliano I already picked on. Luna, come on up. Yeah. Write the augmented matrix for matrix 2, or problem 2. Words are hard. There's the erase button off to the side, and then the fat end of the pen. Yeah, there you go. Ooh, if it's missing, what's its coefficient? 0. Yeah, yeah, good. It is a 5. That's just how he writes his 5. Snaps to Luna. Very good. And I'm glad Luna brought that up. So if a letter is missing in an equation, it has a coefficient of 0. It still needs to show up in the matrix. It's just nothing. Good. Very good. All right, now we're going to practice going backwards. You're given an augmented matrix. What does this system of equations look like? So I'm going to do the first one. I'm going to have you do the second. Remember that if we're given a matrix, the left side is the variables by column. So this is my x column. That didn't come out right. There we go. This is my x column. This is my y column. What does the right side of the matrix represent? The constants, the answers on the right side. Yeah. Good. So for this system, my first equation has 0x. Do I need to write an x down? No, that second equation is just -4y equals 1. Second equation, I have 1x. Yeah, good. I'm not going to write the 1. It's just x minus 5y equals -3. Yeah. Good. Good. Take a second, do number 4. Give you about 90 seconds. And yes, I will use that random name selector again. It's good for you. Is that a little squid or an octopus? Down here. It's cute. It looks like a little octopus. All right, Eunice. Come on up. You can do it. I am confident you can do it. Thank you. Snaps to Eunice. Very good. The only question is thumbs up if we agree, thumbs down if we don't. And I see thumbs up. Very good. There are places where I see a 1 in front of a coefficient. Do I need the 1? No. So if you wrote just x plus 9y minus c, that's also fine. Good. And you'll notice where there was a 0, there's a missing y. Very good. Yeah. Okay. Comfortable with augmented matrices? Thumbs up, sideways, thumbs down. I see nodding and thumbs up. Good. Okay. Now, we talk about the slightly more difficult part, which is now that we've got our system of equations in a matrix, how do we use the matrix to solve? I'm going to show you the long way, and then I'm going to show you the short way. I want you to see both. You should be able to do both. Yeah? So, the goal to solving an equation is to rewrite our augmented matrix in something called reduced row echelon form. RREF. RREF. That's how you're going to see it on your calculator. RREF. Reduced row echelon form. And reduced row echelon form generally contains only 1s and 0s. The first non-zero value of the row is a 1. All of the entries other than that are 0, meaning each entry is only going to have one number in it, or rows each have one number in it, and it's a 1. And they are written in order, so the leftmost one is at the top of the matrix. And I'm going to give you some examples because I think visually it's easier to see than it is to hear. It makes sense in your head when you see it. So an example of a reduced row echelon form matrix. We'll do a super boring one first. That is a reduced row echelon form matrix. We go down the list. It only has 0s and 1s. Yeah? In each row, the first non-zero entry is a 1. I stack them so the leftmost one is at the top of the matrix, and then in decreasing order. So the 1 should trickle down this way. Another example, what happens if my matrix isn't square? Could look like that. That's okay. If your matrix isn't square, it can still be reduced row echelon form. For us, what we want is we want the coefficient part to be reduced row echelon form. And then we want numbers over here. And the reason we want that is if I look at what that says in equation form, this says 1x equals a number. I've solved for x. This bottom row represents 1y equals a number. I've solved for y. So what we are doing is actually just writing the coefficients in reduced row echelon form. And then whatever happens to the answers, that's going to be our solution at the end of the process. So everything we're doing, we are focused on the left half of the matrix. We want the coefficient part to be reduced row echelon form. There is a pattern to doing this. So my suggestion is that you follow my step list, because if you do this in an organized way, it's usually only a couple steps. You make a little loop around your matrix to get the ones and zeros in the right spot. Yeah? Okay. So, in order to do this, we are going to perform row operations on the matrix. Row operations change the row. There is a limit to what I am allowed to do to the rows and still keep the system of equations that it represents the same. We have rules. There are rules for row operations. So, the three things I am allowed to do to my matrix that preserves the system of equations that it came from. First, I am allowed to interchange any two rows. I'm allowed to switch their position. I can move the bottom row to the top, or the top row to the bottom, or the middle row to the bottom. I can move the rows up and down, as long as I move the whole row, everything in it. You switch any two rows. Yeah, mix and match. I can multiply a row by a constant. It would be the same as multiplying the left and right side of an equation by the same number. Thank you. And yes, she did. The last is I am allowed to do a linear combination of two rows, meaning I can add the multiple of one row to another row. We do this when we do solving by elimination. I multiply a row by a constant or an equation by a constant. I add it to the other row. That's all we're doing. When I say multiply, remember that includes divide, because dividing is multiplying by a fraction. So multiply and divide go together. So I can multiply or divide a row by a constant and then add or subtract it to another row. And again, when we're doing these row operations, we are focused on the coefficients. I want the coefficient part, the left part of the matrix, to be reduced row echelon form, ones and zeros. So I am going to walk you through the steps that I do to do this process. And I'm going to do it on a simple equation of just two equations with x and y. Two variables, two equations. That's the most common we're going to see. Deep breath. What I typically do is when I do this, I work in a loop. I'm going to start here. Why is my colored pen not working today? Come on. There we go. So I start here and I loop around this way. So I start by fixing that very first entry and making it a 1. And then I move down and make it a 0. I move over and make it a 1. I move up and make it a 0. There's a loop. So the first thing I'm going to do is I'm going to use multiplication or division to turn that first entry into a 1. So if I had A1 is 3, I'm going to divide that whole top row by 3. If A1 is 2, I'm going to divide the whole top row by 2. If A1 is 1/2, I'm going to multiply everything by 2. So multiplying or dividing that first row to turn the very first entry to 1. Because that's reduced row echelon form. I want 1, 0, 0, 1. Once this entry is a 1, I can then multiply it by whatever's down here and subtract the rows to turn a 2 into a 0. Once a 2 is a 0, I'm going to turn B2 into a 1 by repeating step 1. And then I'm going to turn B1 into a 0 by repeating step 2. A loop counterclockwise around that matrix. That probably sounds scary and intimidating, so I'm going to show you with some examples, because I think once you see it, it'll be less scary. Yeah? So I need you to take a deep breath. Right? You guys can do this. We'll do it together. We can do this. All right, did I put examples here? No, examples on the next page? Yeah? Okay. All right, so in order, write your augmented matrix. Yeah? Turn the coefficients into reduced raw echelon form. Write out your solution. That's what we're doing. So first step, I'm going to write out my augmented matrix. Can I get a hand? Does somebody see what my augmented matrix will look like? Allie? Can I get a thumbs up if you agree with Allie? Snaps to Allie. Very good. And then we start the process. And the process is I'm only looking at the left half, this 2 by 2 coefficient matrix, and I start in the upper left corner. What do I have to do to that first row to turn the first entry into a 1? Divide by 2. Perfect. So I'm going to write an arrow, and above that arrow, I'm going to write what I'm doing to that row. I am taking row 1, and I'm dividing it by 2. And then I'm going to write the new matrix. I'm going to write the bottom row first because I only touched row 1. And then I'm going to rewrite the top matrix after dividing everything by 2. So 2 divided by 2 is 1. 3 divided by 2 is 3 halves. 6 divided by 2 is 3. I think I did that correctly. I see some nodding. Good. Perfect. Quarter of the way done. And remember, we're working in this order. So the next thing I want to touch is the 1 on bottom. What do I want to turn that 1 into? A 0. Yeah. So the question is, what do I do to my matrix to turn the bottom row into a 0? And the answer is I'm going to take row 2 and I'm going to set it equal to row 2 minus row 1. Because I'm allowed to multiply a row and then add or subtract it to another row. So I'm taking row 1, multiplying it by -1, adding it to row 2. For this transformation, which row will be changed in my answer? Row 2. Row 2 is changing. So row 1 stays the same here. I'm modifying row 2. And then we do some math. And you can write it on your scratch paper or do it in your head. But I'm just doing row 2 minus row 1. So bottom minus top. 1 minus 1 is what? 0. That's how we know we did this right. Good. Slightly trickier. -1 minus 3 halves. So I know 1 is 2 halves. So minus 2 halves minus 3 halves. 5 halves. Yeah, -5 halves. Good. And I have to do the same thing with the answers. So 1/2 minus 3. In mixed numbers, that's 2.5, right? I'm subtracting half from a 3. And it's negative 2.5, which would be negative 5/2. Yes? Yes. Because 3 is 6/2. 1/2 minus 6/2 is negative 5/2. Pretty sure I did that right. Halfway done. Halfway done. Okay. I've done the first column. I'm now at this bottom row here, row 2, column 2. And I want to turn it into a what? One, zero, zero, one. Row echelon form should have ones along the diagonal. So I want a 1 down in this corner. The question is, how do I undo negative 5/2 and turn it into a 1? I multiply it by its reciprocal. That's how we undo fractions. So I'm going to take row 2, and I'm going to multiply it by the reciprocal of 5/2. What's the reciprocal of 5/2? 2 over 5. So times negative 2 over 5. Which row is not changing? Row 1. So I'm going to copy row 1. 1, 3/2, 3. And then I'm going to multiply row 2 by negative 2/5. Not too scary. Anything times 0 is 0. Negative times negative becomes positive. And then 2/5 times 5/2. 2 times 5 is 10. 2 times 5 is 10. 10 over 10 is 1. And because this is also negative 5/2, this is also 1. Almost done. One more entry. For reduced row echelon form, diagonal is 1s, everything else is 0s. I need this upper right corner to be 0. So I'm modifying row 1. So row 1 is going to be old row 1 minus, and then I want to multiply this by 3/2 to turn it into a 3/2. I'm modifying the bottom row so that term matches that term, and then I'm going to subtract them to cancel them out. Which row is not changing? 2. I'm modifying row 1. So this is going to stay 0, 1, 1. And then for the top, I am taking 1 minus 3/2 times 0. Well, anything times 0 is 0. 1 minus 0 is 1. Okay, next one. 3/2 minus 1 times 3/2 should be 0. Because that's what we wanted. That's why we did this. Okay, next one. We have 3 minus 1 times 3/2. And I'm going to write that down here. So I have row 1 was 3 minus 1 times 3/2. If I wanted to write 3 in terms of halves, what is 3 times 2? 6. So 6/2. 6/2 minus 3/2 would be 3/2. Yeah. Pretty sure this is just 3/2. Is the coefficient matrix in reduced row echelon form. I see some nodding. This means I'm done. I just have to write my answers. Yay. So first equation. what does this row represent in equation form? One x equals 3/2. Yeah, and I'm going to skip the 1. Perfect. Second equation tells me what? Y equals 1. Yeah. Done. Done. Perfect. We're going to do one more longhand. We'll do a couple shorthand. Yeah? Okay, this one I'm going to have you help me. All right, next example. Example 6 says 2x plus y equals 1. 4x plus 2y equals 6. So first step is augmented matrix. Owen, what is my augmented matrix going to look like for this guy? Thumbs up if you agree. I see thumbs up popping out. Good, very good. Snaps to Owen. Perfect. Okay. Where do I start? I heard somebody mumbling 2. Yeah, we start up here. We work our way around. 1, 0, 1, 0. 1, 0, 1, 0. Work my way in a circle. 1, 0, 1, 0. So the first question is, what am I going to do to that first row in order to turn the first entry into a 1? Yeah? 2 divided by 2 is 1. Probably the fastest way to do it. Which row stays the same? Bottom. Very good. So 4, 2, 6. And then I do the multiplication across row 1. So 2 times a half is 1. 1 times a half is a half. 1 times a half is a half. Do we agree? Everybody looks like they've gone to sleep. Sad face. Okay, so I'd like you to take a second in your small groups. And we're focused on the first entry in row 2. What do I want to turn it into? A 0. Discuss with your table mates. How am I going to turn that bottom left corner into a 0? Give you about 90 seconds. So close. But if I just did row 2 minus row 1, 4 minus 1 is 3. So I need to multiply by row 1 by what? 4. Because then if this is 1 times 4 is 4. 4 minus 4. I would do row 1 times 4. So row 2 minus row 1 times 4. So multiply the top row by 4 and then subtract it from the bottom row. Yeah. So I've seen a couple of solutions. I know Cecil had row 2 is going to be row 2 minus 4 times row 1. Multiplying row 1 by 4 and then subtracting it from the bottom. We're going to try it. Which row is not changing? The top. The top. Better? I could see us squinting. So I'm going to write 4 times row 1 above row 1, just for clarity. So 1 times 4 is 4. 1/2 times 4 is 2. 1/2 times 4 is 2. And I'm doing bottom minus top. So 4 minus 4 is, oh, and this is the same. Nobody knows what 4 minus 4 is? 0. Good. 2 minus 2 is 0. 6 minus 2 is ooh, we have a problem. We have a problem. I can't have 0 equals 4. This is not a true statement. 0x plus 0y cannot equal 4. What does that tell me about my system of equations? There's no solution. If there's no solution when I graph those, what I expect to see is that the lines don't cross. If I were to graph them, I should see 2 parallel lines on my graph. Good. So it is possible you're going to get to a point where you get something in your equation or your matrix that doesn't make sense, 0, 0 number. So if one of those variables drops out, you should be slightly concerned. Good. Yes. Yes, yes, you may. It would be okay if we had 0, 0, 0. That's a true statement. But I had 0, 0, 4. That makes me nervous because that's not true. Okay, let's try one more. It's good practice for us. I think we'll get to the long method on Monday, or the short method on Monday. We're doing the long method first because your Delta math for the week is going to ask you to do what we've been doing. They're going to ask you to set up the augmented and then tell it, what are you going to do next to change your matrix? What are you going to do next to change your matrix? So augmented matrix for this guy. Do I have a volunteer before I pull out my random name generator? Ziza? Good. Perfect. Perfect. Ooh. Cecil's on fire today. So Cecil says take row 1, divide it by 3. Which row is not changing? Second one. So 6, 8, 24 stays the same. 3 divided by 3 is 1. 4 come on, pen. 1. 4 divided by 3 is 4/3. I can't make that any prettier. 12 divided by 3 is 4. Yeah, good. Perfect. Next, I want to turn the bottom first entry into a 0. You may have noticed a pattern. We're taking row 2, and then we're either adding or subtracting something from row 1 to it. So row 2 equals row 2 plus or minus something row 1. What do I need to multiply by row 1 to turn it into a 6? 6. And I want to make it negative because I need negative and positive to cancel. Good. So row 2 minus 6 row 1. I'm going to write 6 row 1 on top, and then we will just subtract. So 1 times 6 is 6. 4/3 times 6. 6 divided by 3 is 2, so that should just be 8. 6 times 4 is 24, right? Ooh, that's fascinating. When I go to subtract, 6 minus 6 is 0. So 0. 8 minus 8 is 0. 24 minus 24 is 0. That bottom row doesn't have any variables, but is it a true statement? Yes. If you get to a stage where you only have one row, what that's telling me is that both equations are the same equation. Both of these equations represent the same line on the graph. And if I look at my original matrix, I can see that really clearly. 6 is 2 times 3. 8 is 2 times 4. 24 is 2 times 12. That bottom row is just double that top row. Those equations are the same graph. If I have two lines that are the same line on the graph, how many solutions do I have? Infinitely many. If I get to a place where I have one row with numbers and one row with nothing, infinitely many solutions. Good. In your Delta math for the week, you're going to practice this step-by-step process. There's only a couple to practice. When I see you on Monday, I'll show you how to do it on your calculator. Yeah? I'm also out of my... Oh, I forgot to stop the recording. Oops.